Let's break down the core idea behind this paper, DeepSeek-V4, towards highly efficient million-token context intelligence from DeepSeek AI. A million tokens. That's a stack of context taller than most entire novels, handed to a model all at once. Every file in a codebase, a year of chat history, a pile of research papers. The dream of an AI that reasons over that much at once keeps smashing into the same wall. Attention gets catastrophically expensive as the context grows. DeepSeek-V4's whole mission is to knock that wall down, to make a million-token context not a heroic one-off, but something you run routinely. And it pulls it off while using a small fraction of the compute and memory its predecessor needed. Here's the wall. In a normal transformer, every token has to attend to every other token, so the cost grows with the square of the context length. Double the context, quadruple the work. At a million tokens, that's astronomical. And there's a second cost, the KV cache. The model's running memory of every past token keeps growing, eating gigabytes of GPU memory just to remember what it's already seen. Together, those two are what make long context a luxury. But long context is exactly what the frontier now needs. Reasoning models that think for pages, agents running for hours, analysis across whole document sets. So the question is, how do you keep a million tokens in mind without paying a million tokens worth of cost? DeepSeek-V4's answer is to stop treating all that memory as equally precious. The KV cache is where every past token is stored for attention to look at. So if you shrink and prune what's in there, everything downstream gets cheaper. V4 uses a hybrid of two compressed attentions in different layers. The first is compressed sparse attention. It does two things at once. It squeezes the KV cache down along the sequence, compressing runs of tokens into leaner summaries, and then it attends sparsely, letting each new token look at only a selected handful of the most relevant past chunks instead of all million. Compress the memory, then read only the parts that matter. The second flavor is heavily compressed attention. This one compresses the KV cache far more aggressively, a tiny, dense summary of the whole past. But then it attends to all of it, because now there's so little to attend to. One keeps detail but reads sparsely. The other reads everything but keeps almost nothing. Stack both kinds through the network, and you get the best of each. The model still sees the whole million-token sweep, but the compute and the memory collapse to a sliver of what full attention would demand. The second upgrade is quieter, but clever. It rebuilds the residual connection. Every deep network leans on residuals, the little shortcut that lets a layer add its update on top of the input, so signals and gradients flow cleanly through hundreds of layers. V4 replaces that single shortcut with hyperconnections. Instead of one stream running through the network, several parallel streams, with the layers learning how to mix between them, a richer set of highways for information than a single lane. The catch with giving a network that much freedom is that it can wander off and destabilize training. So they keep the mixing manifold constrained, mathematically reined in, so the streams stay well-behaved. Stronger information flow, without the instability that usually comes with it. The third upgrade is the optimizer, the algorithm that actually turns gradients into weight updates. For years, almost everyone has used Atom and its cousins. V4 switches to a newer optimizer called Muon, which conditions those updates more carefully, and in practice converges faster and trains more stably at this scale. Faster convergence means fewer steps to reach the same quality, and on a model with over 1 trillion parameters trained on 32 trillion tokens, that's a very large amount of compute and money saved. A small change to the update rule, a big change to the bill. The efficiency engine, in their words. If making a million token context actually affordable is the kind of engineering you're here for, like, subscribe, and pass it to the friend still hitting context length exceeded. Put it together, and the long context numbers are the headline. At a full million token context, DeepSeek-V4 Pro runs each token for just 27% of the compute its predecessor needed, and holds its memory in 10% of the KV cache. The lighter flash model pushes that to 1/10 of the compute and 7% of the memory. That's the difference between a million token context being a stunt and being routine. And it doesn't trade away smarts to get there. In its maximum reasoning mode, it sets a new bar among open models and goes toe-to-toe with the frontier closed models, Gemini, GPT, Claude, on reasoning, coding, and agentic tasks, while being the one that can actually afford to think across 1,000,000 tokens. The efficiency win. So the recipe for affordable million-token context, attention's quadratic cost, and a bloated KV cache are what make long context expensive, so shrink what attention has to look at. Blend two compressed attentions, one that squeezes the memory and then reads only the relevant chunks, and one that squeezes the memory even harder and reads all of the little that's left. Upgrade the plain residual into constrained hyperconnections for richer, stable information flow. Swap in the Muon optimizer for faster, steadier training. The result: frontier-level reasoning that keeps 1,000,000 tokens in mind for a fraction of the cost. The one-line version, DeepSeek-V4, makes 1,000,000 token context routine by compressing and pruning what attention has to remember, so it can think across a novel's worth of tokens at a fraction of the compute and memory. The theme across these DeepSeek papers is the same, and I love it. The frontier isn't only about training a bigger brain. It's about refusing to pay full price for the obvious approach. Full attention over 1,000,000 tokens is the obvious approach, and it's ruinous. So they asked which parts of the past actually deserve full attention, and the answer turned out to be, not many. That's my read. Tell me yours. Until next time.